Example 2. Here a simply support, here should be a cantilever beam, okay? Cantilever. A cantilever beam shown consists of a section with I value that has been given, and the modulus E is given. So for the loading shown, determine the beam deflection at point B. Right, so we're determining the deflection of the free end of a cantilever beam, and the length has been given, the concentrated load M is given, and distributed load is given. So here this cantilever is subjected to combined loading of a distributed load W and a concentrated bending moment M0 at the free end. So obviously we can split them into two cases. In the case 1, it's a cantilever only carrying the distributed load W. In case number 2, it's only subjected to concentrated bending moment M0. So you will have two components of the deflection at the free end, the delta 1 and delta 2. Okay, we're determining these two components, then add them together, we will get the results. Okay, but first of all, you can see that in the data that has been given, you have mm, have gigapascal, you have meter, kilonewton meter, and kilonewton meter. So we need to convert them into consistent units. Okay, now here we're using this most frequently used unit system. It is millimeter Newton MPa system. Okay, so our W will be 20 kilonewton per meter. That is 20 Newton per millimeter. Okay, our M0 equals 80 kilonewton meter. That is 80 times 10 to the 6 Newton millimeter. Now our L equals 3 meter. That is 3000 millimeter. Now our E, the modulus, equals 20 gigapascal. That equals 2 times 10 to 5 megapascal. Then we can start to examine the beam number 1. Okay, so for beam number 1, that is a cantilever only subjected to distributed load W. And we're determining its deflection at the free end. So we turn to the table, and we can find this case here. This is our case 1. And the deflection at the free end, as we just derived in example number 1, we can just directly use equation 29. Okay, here the delta at x equals L equals negative WL force over 8 EI. Then this is based on equation 29. Okay, so we can use these numbers to get the results. We get a negative 20 by 3000 to the 4th over 8 by 2 times 10 to the 5th by 276 times 10 to the 6th. Right here we can get a result that is negative 3.695 millimeter. Okay, this is our beam number 1, and you have calculated that the deflection of beam number 1 at this free end here is negative 3.695 millimeter. Then we can look at beam 2. Beam 2 is a cantilever subjected to a concentrated bending moment. Let's turn to this table. We can find this is our case 2. Okay, a cantilever beam subjected to a concentrated load. If we only care about the maximum deflection at the free end, we can directly use this equation, equation 26. Okay, here delta x equals L equals negative m L square over 2 EI. This is our equation 26. Okay, this can be calculated as negative 80, and where's our values? M0 equals 80 times 10 to the 6 by 3,000 square over 2 by 2 times 10 to the 5th, and 274 million. Okay, here the results will be negative 6.569 millimeter. So this is the result here. Okay, this is the deflection at the free end when this cantilever is only subjected to the concentrated bending moment M0. Okay, the final results, deflection at the point B can be calculated by sum them together. Sum these two values together. Here is the first value, second value. It equals negative 3.695 minus 6.569. And that is negative 10.264 millimeter. And the negative sign here denotes that this deflection is downward.